Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, you'll learn how to do three-dimensional reconstructions of electron density from SAXS data using the DENSS method in RAW. This tutorial requires the RAW tutorial data, which is available on the RAW website. For this tutorial, we're going to use the data in the Reconstruction data folder. If you've already done the tutorial for the Bayesian indirect Fourier transform method, aka BIFT, you should have saved a glucose isomerase.ift file, which you can see here. If you haven't done that tutorial yet, you can open the GI complete folder and find the glucose isomerase IFT file there. Alternatively, the DENSS method also works with PVR functions generated from genome, so you can load in the glucose isomerase.out file if you prefer. I'm going to go ahead and load in the glucose isomerase.ift file. This will load in the PVR function from BIFT for glucose isomerase. You can see that plotted here, and you can see it shown in the IFT control panel. In order to start using DENSS, we're going to right-click on glucose isomerase on the item in the control panel. We're going to go to electron density DENSS in the right-click menu, and then we're going to select that. That opens the DENSS window. What you'll see here is you'll see the controls for DENSS. Once we get it set up and it runs, the results will be shown in the Results tab. So, a brief word on these three-dimensional reconstructions. So for electron density, the three-dimensional reconstruction is yielding actual electron density of the macromolecule instead of just a bead model, which means that it can model internal structure to your macromolecule if you have good enough information. In this case, we want to use the entire range of Q that's available for our experiment, as opposed to truncating to 8/Rg like we do for bead models. This is because we can model in with different densities nominally internal structures inside the macromolecule. Usually the resolution isn't high enough to actually see that, but in theory it can be done. So additionally, similar to bead models, you can't generate a unique reconstruction of the electron density. And so what we do is we generate a number of reconstructions. 20 is usually a good place to start. And then we average those all together, and we create a consensus model from that average. One of the other advantages of the electron density models is they can easily model in different types of density in your systems. Bead models struggle when you have more than two types of density, for example, usually water and your protein. Here we can easily model in water, the hydration layer, lipids, and things like that. So it's a more versatile method in that way. The other thing I need to note is that the DENSS method wasn't originally developed in RAW, and so if you use this for your analysis, you should cite the appropriate paper. That's given down here by the How to Cite button. Pull it up, it'll give a link to the paper, and it also gives a link to the original website for DENSS, which you should check out for more information on the technique and also some tips on how to visualize the results once you have actually calculated them. So we're going to go ahead and get all the settings set. First off, when we generate 20 models, we generate a lot of files, so we're going to make a folder for it. Here I'm going to make a GI DENSS folder. 20 reconstructions is fine. Slow mode is good for what we're going to do. I recommend that for the final reconstructions for a paper. We're going to average the densities once we're done. We're going to refine that average. And we'll align the final output to a known high-resolution structure of the macromolecule so we can compare them. In this case, we're going to use the PDB file in the GI complete folder, this one XIB former. This is a high-resolution crystal structure of glucose isomerase that's been put into the tetrameric configuration that's seen in solution. There are some advanced settings you can change here if you like, but otherwise, we're ready to start the reconstructions. So I'm going to go ahead and click Start. This is going to run the density reconstruction algorithm. You can see the output in the log file here. Once it's run all 20 reconstructions, it'll then do the average, and then the refinement, and then the alignment. On some machines, it's able to do multiple runs simultaneously. At the moment, for technical reasons, this isn't possible on Mac, but on Windows and Linux, you can do it. This is going to take a little while to finish, so we're going to take a bit of a break now, and then we'll pick it back up once we have the results. Once all of the DENSS calculations finish running, the window should automatically show the Results tab, which you can see here. In the Results tab, you'll see a number of different things. I'm going to go through them quickly and then come back around and walk through what is interesting about each one. So if we had run DENSS on a genome-produced IFT, a .out file, we would see at the top the ambimeter results. Because we used a BIFT-produced IFT, the .ift file, ambimeter can't be run on that, and that's not shown here. We then see the real space correlation scores, the reconstruction resolution. These are shown if you've done an average. And finally, we have a summary list, and then results for each individual model, plus results for the average and the refinement. So coming back and going through what these are, just a little bit. So for the mean RSC, this is the average correlation score between all the different models. And this is the standard deviation of the correlation score between all the different models. This then tells you how many of the models were included in the average. In this case, only one model wasn't included, which is pretty good, and that's because in this case the standard deviation is actually quite small, so even though all the models are very similar, one model happened to be outside of the acceptable range. When you're doing the average, it does a Fourier shell correlation, and based on that it estimates the resolution of the reconstruction. In this case it came up with about 28 angstroms for the resolution. This mostly is just to remind you that these are low resolution reconstructions, and so you should only be looking at kind of the broad overall shapes. Small deviations in the shape are not significant. In the summary tab we have a line for each model, plus a line for the refined model. There's a chi-squared. Because the fitting is done against smooth data, the chi-squared actually ends up being quite small. This is something that if you're interested in, you should talk to Thomas Grant, who came up with the DENSS method about. Next, you'll see the radius of gyration calculated for the model. This should be close to what you get for the Guinea and P of R radius of gyration. And we have the support volume for the model, which in theory should be similar to the overall volume of the macromolecule. And finally, we show the mean RSC. Essentially, mostly what we're looking for here is that the RG is consistent with what we expect, and how many models we've accepted, and if this average real space correlation is relatively close to 1. In each of the model summary panels, then, you'll see the model data, the smooth model data. The scattering from the density is the red dots, and then there's model data plus the extrapolation shown in the blue dots. You can see it fits quite well. Here again, the residuals are quite good, though there is a little deviation on the very last point. These plots here on the right, all three of them, show the convergence of the chi-squared, the RG, and the support volume versus step number. What you're looking for is that by the end of the run for the model, this is actually converged to a single value, which you can see that it has in this case. And you can look at that for each model that we've run. So in the average tab, you'll see the Fourier shell correlation. We use this to estimate the resolution. We look at where this crosses 0.5, and then get the resolution in real space by just doing 1 over the resolution at that point. The refinement shows the same thing as the other models. You can see the convergence plots, you can see the data and the extrapolation, you can see the residuals. So going back to the summary tab, all of this information, as soon as the calculation finishes and we generate this results list in the results window, it's also saved in a CSV file in the folder, your output folder, so that you can load these back up and take a look at them whenever you want. So I'm going to take a moment now to look at the results in the folder, the output folder. So you can see here this GI DENSS folder. So there's a number of files in here. So you can see for each model that we generated, there's the prefix, then underscore the model number. So this is going to go from 01 up to 20, which you can see here. For each model, the o1.mrc and o1.explore represent the final electron density maps. They're just two different formats of saving those. The log file is what we saw in the tabs of the run panel as each dense run was running. And then you can get information about the support and the stats by step and things like that. These are all things that are included in the summary panel, but you can extract them from here if you want as well and plot them in your own data. So in addition to each individual model, if we ran the average, we also have this average file here, which has the log and the MRC and the FSC, the Fourier shell correlation. If we then further ran the refinement, you can see that there's the refined results here. Again, the refinement MRC and Explore are the ones of interest. These are the final electron densities. Finally, if we ran the alignment as well as all of the rest of it, some of the files will have this underscore aligned. So in this case, the only file that we've aligned is the refined file. You can see this aligned.mrc file. If we didn't have a refinement, it would align the average. If we didn't have an average, it would align each individual model. So it depends on what you've produced as part of your data set. The final files that I want to point out, so there's the CSV file, which I mentioned previously. If I open this in Excel, you can see that this contains the real space correlation results, the reconstruction resolution, the individual model results, and some information about our input parameters. The PDF file is just the plots that we had in the individual tabs. Saved for your convenience. These can also be recreated from the files in the folder if you wish. Once we're done, we can just close this. None of the information is saved with the IFT because there's too much, but it is all available in that folder. With that, that's the end of the tutorial. You should now know how to create electron density reconstructions in RAW using the DENSS method.